All right, last video. So I'm going to do this problem, then I'm going to show you one more example that will be helpful to you when you get going on your homework. But this particular problem is very much like the last one we did. Okay, in this, I mean, it's really not a lot different. And I kind of debated doing a video on it or not. And I thought, well, so we've got these two masses on there, and this thing has a torque, and so it's trying to rotate like this. And they actually tell us the amount of the moment on this one, and it's going to go for 4 seconds. I don't know why this chapter is obsessed with 4 seconds. Then what's different is we also have this thrust acting somehow, and somehow that thrust is always perpendicular. Okay, so which is very convenient. But we're going to take the same approach to this situation. All right, so for an object moving in a circle, we can say the angular momentum is just this value right here. And so that means that our velocity is going to be h over rm. All right, so if we find h, we're good to go. So our h, to find h, we're going to come through here, do the same thing, dt. Okay, now the motion is all in a plane. That means all the angular momentum and the moments, the values and all that, they're all perpendicular. They're all in the z direction. I'm going to drop the vector notation on it here. Okay, and we're going from 0 to 4. And we've got this 8t, but we've got that thrust that's on there as well. Okay, got the thrust on there as well. And so what I'm going to do is we got to put in the thrust for both objects. So that's a total of 20. Okay, and so the radial value there is 0.5 times 20. Okay, so that's my moment due to the thrust. Okay, and again, do this integral by hook or by crook, however you want to get it is just fine. But what it turns out to be is 104. And that's kilogram meter squared per second, just like so. Okay, and that, of course, is my h final minus my h initial is 104. We're starting from scratch, and so 104 is the value for h. Let's go back then up above where we said v is h, which we've got 104 kilogram meters per second square, meters squared per second, divided by a radius of 0.5 kilograms. Woo! 0.5 meters. Sorry about that. 0.5 meters. And our mass is 20 because we've got two of these objects. Okay, so we got to take into account the whole thing since we did that. All right, and anywho, what happens there is we get 10.4 meters per second. All right, so there's that one. Okay, now I want to do another example for you, and this is going to come into play in your as you're working on your homework. So let's suppose that we've got a smooth disk, okay, and it's stationary, but there's a mass on the disk here, and there's a string, all right, that goes through there, and we've got some tension there pulling that thing. Now, what's going to happen is the tension, we could either pull that thing, which would make the radius get smaller, or we could sort of let it be a little bit lax, and you can imagine it's going to have to get bigger. What we would like to know is what happens to the velocity of our mass there as we either pull on that string or loosen that string. Okay, either way. So the way we do this is by realizing that when it comes to our impulse here, that in a case like this, my velocity is here, okay, but the force that I have acting on it is here, and my radius is here. So as I'm pulling on that string, there's no moment going into that thing. And so actually this term right here is 0. Okay, so that term is 0. And that means then that my change in angular momentum is 0. All right, so HF minus H initial is 0. And so we see that angular momentum, like I mentioned earlier, is preserved, whatever we have right there. Okay, and so what we can do then is we can say, well, my initial angular momentum was whatever my initial radius is, mass, and my initial speed. In the end, I've got some final radius, the same mass, but a different speed. That's an R, by the way. Okay, and you can see there then that we're going to lose our mass values. Boom, boom. Okay, and our final velocity then is proportional to our initial velocity according to the ratio of the radii. All right, so Ri over Rf, just like that. Okay, so if you cut the distance between the hole and the object, if you cut that in half, it's going to double the velocity. So it's going to go twice as fast. If you lengthen it out, it's going to go longer. Okay. Now, a famous example of this really is Planetary Dynamics. How about that? See, now you can tell your parents that you're studying rocket science. Okay, you can do that. Tell your grandma and grandpa you're studying rocket science. Okay, so let's suppose that this is the sun, and we got the Earth, and the Earth is going around, woo, like this. Okay, now you can see the sun is offset. Okay, because the Earth actually moves in an ellipse, and the sun is the focus of one of those ellipses. Of that ellipse. It's one focus of the ellipse. And so the Earth, as it's moving around the sun, actually 6 months later, it's over here. Okay. And so the Earth moves more slowly over here and more quickly over here on this side. Okay, as it gets closer to the sun. All right, now in the northern hemisphere, we tilt away from the sun in the winter time. And I think for us, winter time also corresponds to when we are the closest to the sun. Okay, I think that's our situation like that. Please don't quote me on that. Yeah, I should have looked it up, but I'm rolling with it. So anyway, the angular momentum of the Earth is constant, and so we always tilt. Our orientation is the same. Okay, so when people talk about the Earth tilting away from the sun with the different seasons, blah 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 blah, that isn't strictly speaking true. What happens is our position as we go around the sun, our position relative to the sun is what changes, and it gives the illusion that this thing is going back and forth with the seasons. Okay, now we still end up with shorter I mean, the conclusions are all true, you know, shorter days in the winter and longer days in the summer for the northern hemisphere, but the Earth's not really changing its tilt. The Earth always faces the same direction. Okay, but the speed with which we move around the planet or around the sun is going to change, and this is one of the things that Kepler discovered. Okay, so the area over here, if this is 1 week, if it takes 1 week to get from here to here, anywhere on here, if it takes 1 week to go the same distance, okay, that's often called the equal areas, equal times law. That's a consequence of the conservation of angular momentum. Okay, so anyway, fun stuff there. Okay, and the actual shape of our orbit is pretty darn close to a circle, but it's not a circle. Okay, and you'll listen, you're going to hear from time to time people say things like, well, the Earth has to be in exactly a certain position away from the sun. If it was just a little bit too close, we'd burn up. Or if it was a little too far away, we'd freeze. Okay, well, you know, if you know somebody who's saying that, you know, just pull them gently aside and say, no, it's just not true. The Earth moves millions of miles back and forth over the course of a year. Okay. Well, anyway, I'm going to end it there because I'm starting to get long-winded. All right.